Hello, we're Group 2, Section 302, and welcome to our lab quad chart presentation. Our presentation here is broken up into 3 different parts. So for the first part here, we were asked to find the velocity relative to voltage input across the test section given 4 different measurements. This involved taking the partial derivatives of each variable in the given equation and using the general formula of propagation of uncertainty and utilizing the appendix of given values. Next, we were asked to calculate the airspeed at each vertical Y position across the ports along the boundary layer. This gives us the necessary information to calculate the boundary layer thickness, type, and velocity at its edge. These properties suggest which type of boundary layer it is. For example, we know the turbulent flow diverges much more aggressively. So from there, after finding shear stress and boundary thickness, we can reasonably infer which type of boundary layer it is. Lastly, for part 3, we were asked, given an angle of attack, to calculate the pressure value at the trailing edge of the boundary layer. Next, we had to find the coefficients of pressure in order to find the normal and axial coefficients, and lastly, the lift and drag coefficients. We did this by finding the pressure coefficients around the perimeter to calculate the coefficient of pressure at the trailing edge, and then we used the Riemann line sum around the perimeter to find normal and axial coefficients, and used coordinate transformation based on the angle of attack to find the drag and lift coefficients. In sum, we did all of this to take a look at an airstream and how an object interacts within it.
The first section of our lab was the airspeed voltage model development for the wind tunnel. For this section, pressure measurements were taken at different voltage inputs to the wind tunnel using 4 different combinations of pressure measurement and reading devices. Next, we converted the differential pressure measurements to velocities using Bernoulli's and continuity. And we plotted these values to find the relationship. It was found that the relationship between velocity and voltage was a direct linear relationship, and this can be seen in figures 3 to 6. And it follows the equation velocity equals 5.5 times voltage. Next, we calculated the uncertainty in these velocity measurements using the general method and partial derivatives. As you can see with the error bars in the graph, uncertainty decreases as velocity increases. We plotted the uncertainty versus airspeed in figure 7 and found that it is an exponential relationship. We also found that the U-tube manometer is a more accurate measurement device than the pressure transducer, especially at low velocities. Next was the boundary layer analysis section. For this section, airspeed measurements were calculated at various X and Y locations around a flat plate in the wind tunnel, along with free stream velocity. We plotted the airspeed versus Y location, or distance above the flat plate, for various port numbers, or X positions, and this is shown in figure 11. It shows that at an earlier port number, velocity increases faster as you move away from the flat plate than it does at ports farther back. Next, we found where velocity was 95% of the free stream velocity for all the ports to find the thickness of the boundary layer at that port. After plotting this, we've found that thickness increases similar to a square root function. We then compared this to the theoretical models for turbulent and laminar boundary layers and found that ours was representative of a turbulent boundary layer. This concludes the velocity, voltage, and boundary layer section.
For the static pressure portion of this lab, we were given a data set of the static pressure along the circumference of an airfoil at different speeds and angles of attack. From this data, we found the coefficient of pressures at all the given locations on the airfoil, and what we found is as angles of attack increase, the pressure coefficients increase near the leading edge of the airfoil. Additionally, as the velocity increases, the overall pressure increases along the chord length of the airfoil. However, what we also found was as velocity decreases, or as the pitch increases, we see a higher pressure occur at the trailing edge, indicating a separation of the boundary layer. This is due to the adverse pressure gradients occurring at this location, which cause a negative flow velocity over the trailing edge, thus increasing the magnitude of velocity over the pressure port, but still separating the boundary layer. Additionally, the greatest pressure distance or between the top and the bottom of the airfoil happens before or at the quarter chord. This creates an upward moment because of the differential in pressure. In conclusion, flow separation occurs at the trailing edge as velocity decreases or as the pitch increases, and there occurs an upward moment on the airfoil due to the pressures, the sum of all the pressures happening on the airfoil as it goes through an airstream. That concludes the airfoil static pressure portion of this presentation.
In the final section, we'll discuss lift and pressure drag coefficients. Looking at figure 14, we can see a stacked plot for the drag and lift coefficients for an airspeed of 34 meters per second. We can see how these coefficients vary with the angle of attack. We can see similar things in figure 16. We see that on the left we have coefficients of lift, and on the right we have coefficients of drag. We see that these plots are also stacked with different airspeeds respectively, 9 meters per second, 17 meters per second, and 34 meters per second. Overall, we can see that lift increases with an angle of attack about 10 degrees, where a stall occurs. Drag decreases as the angle of attack approaches 0, and then will increase with the angle of attack. You can see that it has a downward trend and then an upward trend, starting at 0 degrees angle of attack. In comparison to the NACA plot, which is on figure 15 on the left, you can see that our plots are very similar in the linear regions, but overall they do differ. We see that our plot shows a sharp leading edge stall, while the NACA plot shows a gradual trailing edge stall. This is one of the major differences in these plots. In figure 14, we can see a lift coefficient at 0 that is at about negative 8.5 degrees angle of attack, which is about at 34 meters per second, which is what figure 14 governs. We see that the lift coefficient does not equal 0 at 0 degrees angle of attack because we are using a positively cambered airfoil. We see that max lift occurs at 11 degrees angle of attack at 34 meters per second, and the angle of attack yielding a lift coefficient of 0 would change with the airspeed depending on what the airfoil sees. The airfoil experiences a sharp leading edge stall, which was mentioned before, and this can be linked to the Reynolds number, which dictates when flow separation occurs. We see that the lowest pressure drag occurs at 1 degree angle of attack. Finally, the lift coefficient is defined at all tested angles of attack, and at 34 meters per second, the coefficient of lift is greater than the coefficient of drag for all angles of attack above negative 9 degrees, meaning we are seeing lift. That is the end of our quad chart presentation. Thank you so much for listening.